Welcome everyone to the second part of our 25th lecture for Calculus 3. In the mad spring term of 2020, this is a lecture that's meant to be viewed on Tuesday, April the 7th. So today we are going to begin chapter 15.6 of Stewart, and this is triple integrals. We're going to begin dealing with the Cartesian coordinate system, and we are going to begin with rectangular boxes. So as usually the case, we're going to begin in easy mode here. We will ultimately have three different coordinate systems for triple integrals. We had two in double integrals, Cartesian and polar. In triple integrals, we will be considering Cartesian and cylindrical and spherical coordinate systems. There are actually others. There's nothing special about having two in 2D and three coordinate systems in 3D. That's just sort of a coincidence here for the ones that we happen to be studying. There are, in fact, infinitely many different coordinate systems that you could study in any dimensional space, and we will think just a little bit about the general theorem which allows us to create new coordinate systems. This is what's known as the change of variables theorem in calculus. So once we wrap up triple integrals and we have discussed cylindrical and spherical coordinates, we'll think just a little bit about the general theory known as the change of variables theorem. It itself is a special case of a more general theorem known as change of measure, but they are not really within the scope of this course, so we'll only glance at them, maybe give it half of a lecture or so before moving into thinking about vector calculus. But let's begin here in the easiest situation for triple integrals. These are triple integrals over rectangular boxes. Rectangular boxes are going to be the collection of all ordered triples in R3, such that x is bounded between two constants a and b, y is bounded between two constants c and d, and z is likewise here bounded between two constants e and f. So the intuition is that we are looking at what you think a rectangular box looks like. It's got a rectangular base, and it's got an identical rectangular top to it, and then there's some height associated with the box, which is given by the bounds on z. So here in our vertical dimension, the height of the box is going to be f minus e, those being the bounds on z. The depth of the box, we might say, is going to be given by the length of the interval where x is allowed to live, b minus a, the difference between the bounds on x. And the width of the box is given by d minus c here, those being the bounds on y. This is going to be, again, the very easiest type of integral, of region rather, that we can take triple integrals over. And in fact, we will see that we do have something like Fubini's theorem for triple integrals. First, the definition of triple integrals over a region of this type is going to be given by triple Riemann sums. So in Calc 2, we studied Riemann sums. Earlier here in Calc 3, we have studied double Riemann sums. We did that in some detail. We looked at pictures. We thought about these little subgrid, or the subregions created by the grid in the xy plane for a rectangle R. And we took the height of each of the little subrectangular boxes to be given by the value of the function at some point within each subregion. You can do something exactly analogous for integrals over regions of 3 space. You can't draw the pictures, and we're going to talk a little bit more about how we lose the ability to draw the pictures of the regions, not of just the region, but of the region together with the integrand here. We'll talk about that in a bit. But computationally, the triple Riemann sums look exactly analogous to the form they took earlier in Calc 3 and even in Calc 2 for single Riemann sums. So you're taking your region, your rectangular box B, you're dividing it up into a bunch of sub-rectangular boxes now. Instead of we took rectangles and divided them into sub-rectangles when we thought about double integrals, now we're taking a rectangular box and dividing it up into sub-rectangular boxes. There's going to be a delta V expression, which is going to look like delta x times delta y times delta z. It's going to be the volume of each of the sub-rectangular boxes. We'll be taking the value of the integrand at some point in each of those boxes. We'll let that be something like height, and the volume here is something like the volume of the base, quote-unquote, for a 4-dimensional volume. But we're multiplying these together, and we're adding up that value for each of the sub-rectangular boxes, and we're taking the limit as our grid becomes infinitely fine. So the limit here is increasing the number of divisions along the x-axis, along the y-axis, and along the z-axis to get a finer and finer grid, and the definition of that limit is the triple integral over b. So if you compare this to what was done for double integrals over rectangles, you will see that they are exactly analogous, except it's a triple sum here where it was a double sum before. And in the limit, the triple sum becomes a triple integral, whereas in the earlier case, in the limit, the double sum became a double integral. So the limit definition is nice, and it does grant us some theoretical insight into what's being discussed here. What is it that integrals really mean? But it is not the tool that we use to actually integrate functions, just as it was not the tool that was primarily used in practical applications for double integrals or for single integrals. Instead, we're actually going to compute triple integrals of this type over rectangular boxes using Fubini's theorem for triple integrals. And Fubini's theorem for triple integrals is going to say, big picture, that the triple integral of f over a rectangular box is going to be given by any of the iterative integrals that you can write down. So here's an xyz, a yxz, there's a bunch of others that we're not going to write out, and we'll end with the zyx one, where the order's been exactly reversed. So that's the idea. Triple integrals over boxes can be found by taking iterative integrals, and you can take those iterative integrals in any order that you prefer. So we will state the theorem formally. If f's map in R3 to R, if it is continuous on a rectangular box of this type, where x is bounded between a and b, y is bounded between c and d, and z is bounded between e and f, then the triple integral of f over b is given by any of these iterative integrals. And note that the limits of integration for each of the variables are the bounds that constrained that variable in the definition of b. So x was taken to be between a and b, and my limits of integration for my dx integral are a and b. And that remains true regardless of where the dx integral shows up in terms of order of integration. It's always going to be paired together with its appropriate bounds given in the articulation of region b. So the first thing to note is that this triple integral can be taken over any or as any of the iterative integrals where the x, y, and z variables show up in any order. How many such orders are possible? So how many cases did I dodge by sticking the ... into the statement of the previous theorem? Well, if you're thinking about it in a sort of combinatorial way, if you've ever heard that phrase before, combinatorics is an area of math that deals with sort of how many different possible ways can things be rearranged, or how many options exist for different scenarios. And if we think about this combinatorially, how many options do I have for which integral is the innermost integral? Well, there are 3 options. Before anything has been decided, the innermost integral could be with respect to x, with respect to y, or with respect to z. So there's 3 options existing for the innermost integral. Once that is fixed, 2 options remain for the middle integral. And once those 2 have been decided, the final integral is already determined. It's the only one that you've got left. There's only 1 option remaining. And so combinatorics tells us in this situation that we multiply the number of options available for each of these choices that could be made, and we end up with a total of 6 possible orders in which these iterative integrals could be written. So this is the concept of permutations. If you have taken my probability and statistics course, or if you're taking it now, we talk about permutations. And this is the permutations are the number of reorderings of the letters x, y, z. So order matters here, the order that they show up matters. And there is 3 factorial, 3 times 2 times 1. We're also using the idea of the multiplication principle if you are taking combinatorics. If you're taking probability and stats, or if you've taken a class on combinatorics. If you haven't, that's okay. You don't actually have to know any of this. It's just a point of interest here along the way. There are 6 different possible ways you could write this. There's xyz, xzy, with x coming first. There's yxz, yzx, those 2 with y coming first rather. And then there's 2 where z come first, zxy and zyx. And 2 plus 2 plus 2 is 6. Fubini's theorem is telling us that all 6 of these iterative integrals are equal. So if you compute this triple integral as any of these 6 iterative integrals, you're going to get the same answer. The second note that we want to make is that we are stating the theorem with a condition that f be continuous. That is certainly enough for the theorem to hold, but it is more than is strictly necessary. So continuity is a sufficient condition for the theorem to hold, but is not actually necessary. The theorem holds for discontinuous functions as long as their discontinuities occur in certain technical ways. The statement becomes dramatically more complex, and we are almost entirely dealing with continuous functions in this course, so we prefer this statement of the theorem. Just state it for continuous functions because the statement is simpler. So let's do one of these. Let's have an example here. So let's let B be a rectangular box where x is between -1 and 1, y is between 0 and 2, and z is between -2 and 3. And we can again write this box as a product of three intervals, just as we did for rectangles in the plane. So the first interval given here is always going to be the interval where x lives, the second will be the interval for y, and the third is the interval that z is constrained to occur within. So these are my bounds for x, for y, and for z. This is the region B. Here's the set theoretic definition. Here's sort of a simpler shorthand statement. And I want the triple integral of integrand x times y squared times z cubed over B. So x to the 1, y to the 2, z to the 3. It looks like a lazy person came up with this problem, and perhaps that is the case. So we're going to find the triple integral of that integrand over region B. I'm going to go ahead and write this as a dx dy dz integral. Again, laziness compels me to obey alphanumeric ordering if I have no preference to do otherwise. X is going here from -1 to 1, y was going from 0 to 2, and the outermost integral with respect to z has limits of integration -2 and 3. This is a case where all of our limits of integration are constant, as it will always hold for integrals, triple integrals over rectangular boxes, but also where our integrand factors nicely as a function of x, a function of y, and a function of z. So I'm actually able to factor this out into three single integrals, just as we did for double integrals when these two conditions held, constant limits of integration, and a integrand which factors cleanly into functions of each of the single variables. So I can perform these three single integrals in parallel here. Z cubed is going to 1/4 of z to the 4th, z squared is going to 1/3 of the cube, and x is going to half of the square here. And we've got our limits of integration. We can plug those in. This one I didn't bother to simplify yet. This one I simplified. It was a bit easier. But the key aspect is that for the square, x squared is 1, x squared at 1 is 1, x squared at -1 is also 1, and their difference gives me 0. So the whole of the integral actually has value 0 here. And as we said, if the limits of integration are constant, and if your integrand factors cleanly in this way, then you are able to pull apart your triple integral into three single integrals. But that doesn't always work. So let's have a look at a sample problem where that's not going to work. So here's B given as the product of three intervals. The first is the bounds for x, the second gives the bounds for y, and the third the bounds for z. Oh, and I pause to yawn. Lots more yawns when I'm teaching this from home than when I'm standing up in front of the classroom. Here's our integrand xy plus z squared. So I want you to take that integrand over this rectangular box B and find the triple integral for me. And I'll go ahead and note for you that this one's not going to factor cleanly the way that the last example did. Instead, we will have to compute the innermost integral first, and then the middle integral, and then the outer integral. We're going to work from in to out, just as we did for double integrals here. So give that some thought, and pause the video, attempt it. You should be able to get a numerical solution, and we'll reconvene in a moment to solve it as a group. Alright, so let's take a look at the solution to this. So the triple integral over B of this integrand, I'm again going to write it as a dx dy dz integral. In the third part of today's lecture, we will consider some cases where you might have a preference for one of the orderings. But for this problem, any of the iterative integrals that you choose should work just as well. So if you do it as a dy dx dz integral, that should be fine. But I'm taking it as a dx dy dz. X was going from 0 to 2, y was going from 0 to 1, and z is going from 0 to 3 here. So my innermost integral is with respect to x. My z and y integrals are going to just wait in the wings here for their chance to come onto the stage. I take an antiderivative with respect to x. I'm getting 1/2 x squared y plus x times z squared. And x is going from 0 to 2. I could write this as x equal to 0 and x equal to 2 if I want to be extra careful as to which variable these are limits of integration for. But I'm bearing it in mind. I'm going to plug this in. The value of this antiderivative at 2 gives me 2y plus 2z squared. The value at 0 gives me 0, so I'm subtracting 0 off, and this is now my integrand of two variables in a double integral, iterative integral with respect to y and then z. So now we're at the point that of a type of problem that we discussed earlier in the term. We dealt with double iterative integrals. I'm going to take an antiderivative with respect to y. 2y comes to y squared. 2z squared will be 2yz squared. This was a constant with respect to y. Y is going from 0 to 1. Again, you could write y equal to 0, y equal to 1 if you want to be a bit more careful with your notation. Plugging these values in for y, the value of this antiderivative at 1 is going to be 1 plus 2z squared. The value at 0 will again be 0. Now I'm left with a single-dimensional integral of a polynomial. This is about as easy as our Calc 2 problems got. I take an antiderivative with respect to z, and I'm getting z. 2z squared is going to become 2/3 z cubed. We're going from 0 to 3 here. I plug in the value at 3, and I'm going to have 3 plus, this would have been 3 cubed over 3, which is just 3 squared, which is 9, times 2, giving me 18. And the value of the antiderivative at 0 is 0. So I've got 3 plus 18, which is 21 for the final value of this triple integral over this rectangular box. And again, we did it with respect to an dx, dy, dz iterative integral, but you could have used any order of integration according to Fubini's theorem, and you should get the same answer. So let's think about the dimensionality here, and let's think about what it is that we're finding with these triple integrals of some integrand over rectangular boxes. When we dealt with Calc 2 style problems, so a real valued function of one real variable. It has one real variable as input, a single number as input, and it spits out a single number as output. Here the domain for such a function was one-dimensional, one real variable. And the graph lied in R2. These are sort of the classic functions that we grew up thinking about in high school and in the early part of our college career. The graph lies in the plane here, and the integral of f over an interval of R1 is an area. So when we take integrals of real valued functions of one real variable, we are in general getting areas in some sense, as we've drawn here. So that's what we're doing in Calc 2. In Calc 3, earlier portion of the course, we took real valued functions of two real variables. Here we were dealing with f of xy. Our domain was two-dimensional in this case. The graph lied in 3 space in R3, and the double integral was a volume in general. Earlier in this lecture, we thought about how you can let little f be 1 and find an area taking such double integrals, but even that area gave the area because it was a particular volume of a region that had height 1 everywhere. So in general, if you have a non-constant surface, f of xy, and it remains non-negative, and you integrate it over some region of the plane, you end up with the volume between that region of the plane and the surface. So with a two-dimensional domain and a one-dimensional output, the graph lied in 3 space, and the double integral of that function gave us a volume. Now we're dealing with real valued functions of 3 real variables. We've got 3-dimensional domains, we have a one-dimensional output here, the real value of the function, and so its graph actually lies in 4 space, and I am not able to draw such things. Now our triple integral of f with respect to volume is giving us some kind of a 4D volume. It's sometimes called a hypervolume, or it might be referred to as well, there's other terminology that I don't want to introduce because I think it might be a bit confusing in this context, but we have left the realm that we are able to think about and draw these things carefully. The idea is that I've got a volume I'm going through every little sub-volume in the region D, some subset of 3 space. So I've got something like a rectangular box here. I'm moving through every point in that volume, and at every such point I'm multiplying the volume of the little sub-rectangular box times a height, quote-unquote, pushing out in the 4th dimension. So it is like height times base again, in some sense, but my base is already 3-dimensional, and then I'm taking a height on top of that 3-dimensional base, in some sense. So we're coming up with 4-dimensional volumes here. The volume of a 4-dimensional object, which is represented by, it has base, quote-unquote, in R3, given by the rectangular box D, and height at every point in D, given by little f of xyz. So it's good to bear this in mind. It's always good to think about what we did and what we're doing now and how things scale up as we increase the dimensionality. And it's also good to recognize that there is a volume associated with a double integral, but you're taking your integral over a 2-dimensional region, and then your 3rd dimension is coming from the height at every point in that region. And that's exactly analogous to what we're doing here. D itself is a volume now, and we've got a height at every point in that volume, and taking that height at every point in a volume is giving us our 4D object, which most of us are not able to picture cleanly. So that is the idea for triple integrals over rectangular boxes. Computationally, it's just as simple as double integrals over rectangles were, except you have to do one more iterated integral in this context. So the next thing that we did when we were working with double integrals was we began to think about double integrals over non-rectangular regions. We had our type 2 and our type 1 regions in the plane, and we learned to integrate over those types of regions where just the outermost integral had to have constant limits of integration, and the inner integrals were allowed to have limits of integration that actually depended on the outermost variable, the variable with respect to which the outermost integral is taken. There do exist analogous situations and analogous types of regions of R3 for triple integrals. So triple integrals over more general regions is a topic that's discussed in 15.6 of Stewart, and you are welcome to look at it. Where we had type 1 and type 2 regions in the plane, you will have type 1, type 2, and type 3 regions in 3 space. And that is because you're going from 2 dimensions to 3 dimensions here, that you had 2 examples and then 3 examples. So this is the topic. It takes a fair amount of work to set up this topic, and you have to think a bit. There's a bit of like mathematical machinery that has to go into this. You have to start projecting into one of the coordinate planes. So you've got your region of 3 space, and you have to project it down into the xy plane, or project it over into either the xz or the yz planes. And so there's just a bit of background and a bit of setup, and it generally takes several lectures to do. I typically devote 3 lectures to this topic, and because we lost 3 lectures in our extended spring break, as the school was allowing us all to try to make this transition to online courses, this is the topic that I'm going to cut from the course. So it's not really critical. Nothing that we do later depends on it. It takes a fair amount of work to set it up and a fair amount of time to cover it. We can cut it out, and we can still hit all of the big ideas of the course in a way that gives us plenty of time to deal with the later material. So this seems to me to be a good place to make this cut. You are welcome to have a look at 15.6 of Stewart, and if you have any questions about the material there, I will certainly be more than happy to talk to you about it. It's not honestly material that comes up just terribly often in my experience outside of being taught in this course, whereas the material that we're going to cover later, thinking about cylindrical coordinates, thinking about spherical coordinates, and certainly thinking about vector fields and conservative vector fields and the fundamental theorem of line integrals, that does come up later for folks, certainly for our electrical engineers, for any of our engineers, and for our math majors. That material is much more relevant once you get past this course. So this is a complex topic that's a bit esoteric and that nothing else depends upon, and so this is where we're going to make the cut for this course. So if you have questions again about that material, please let me know, and I'll be happy to talk to you about that information. We are going to wrap this part of the lecture up now. The final part of today's lecture will deal with some triple integrals over rectangular boxes, where you may actually care about the order in which you perform your iterated integrals. It may actually matter, and some iterated integrals may turn out to be nicer than others. So we'll take a look at that shortly. I thank you folks, and I will see you again for the third part of today's lecture.